Alright, so I'm a little unsure about the order in which I want to present the concepts that we need to present. We sort of have a list of things that we need to talk about in order to kind of get towards the incompleteness theorem. And I think I found a good place to start, and I think that good place to start is this concept of computable enumerability, which is going to be pretty central to everything we do after this. And so I'm going to define this right now, and I'm defining it right now in an attempt to explain in terms that based on what we've said already, kind of arrive at another concept that's very related called countability, and specifically to talk about the concept of uncountability, different sizes of infinity and so forth. But in any case, we're going to start, I think, right here. So let's define it. Oops. So I think this definition will come off simple, and it will gain complexity and complication as this series of videos continues. So a set is computably enumerable, and there's other words for it. You can also call it recursively enumerable or effectively enumerable. As we know, computable, recursive, effective, these all kind of mean the same thing historically. If there exists an algorithm for listing out the elements of the set. Listing out, let's just say listing out the stuff one at a time. So I can give you an algorithm, that is to say, what is an algorithm? It's a finite description of an effective process. I can tell you in a sequence of words or a string what to do, and I can give you a way that if you follow these instructions and just kind of continue to do this on paper forever, you would list out all of this stuff. It would be an exhaustive list. In other words, exhaustive in the sense that anything in the list, even if the set is infinite, everything will be hit on eventually in a finite amount of time. So there's one computably enumerable set that everybody sort of has hardwired into their heads at a very early age. So there's one specific set, enumerable set, for which the algorithm is burnt into our brains from a very early age. And that computably enumerable set is this. And that is the counting numbers, otherwise known as the natural numbers, this thing, n, which is the set 1, 2, 3, 4, 5. See, I'm doing it. I'm doing the algorithm. I'm doing it. Well, and here's the thing, right? So I've gotten to 9, right? I should probably start at 0 this time, just for clarity's sake. So I have 10 digits, and this is the thing. This is why this is an algorithm, kind of, is because we need to be able to count as much as we want. We need to be able to count, we as humans have decided that counting is a useful thing to be able to do, that we teach, our kids how to do. And we need to be able to count as high as we want, and we need a system for doing that. But we don't want to have an infinite set of symbols. So it's really not, so the real set that we are counting through, the real computably enumerable sets, is strings. The real set is strings from the alphabet of digits, essentially. It's not exactly this set, but i.e. the alphabet. Remember, we use the Greek letter sigma, which we use the Greek letter sigma to denote an alphabet, which is exactly these numbers here. We've got 10 digits, right? So this is the entire alphabet, and we want to be able to we want to be able to count forever with just these 10 digits. And so when we get to 9, when we get to the last digit, or what we've decided is the last digit, what do? Well, we flip that 9 back to a 0, and we add another digit. And we have this thing called 10. And then we start counting again. We leave the 1 alone, and then we kind of keep going. 11, 12, 13. I mean, the words don't matter. I want, like, the words, we've given this thing a name, 13, but what's more important is that we can write this down and know where it appears in this sequence. 14, 15, dot, dot, dot. We get all the way up to 19, and then we reset again, and we get to 20. And then we get to 21, and we dot, 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 all the way up to 29. And then that happens until we get up to 99. And then we're out of digits again, or at least we've listed all of the numbers that we can with this many digits. There's a bit of a complication here in terms of putting leading zeros, but that's, you'll see, it's not that big a deal. It's just we've decided not to do that. So we skip over that we skip over strings that have leading zeros. But other than that, we're kind of just going through all essentially words that you can make out of this set of symbols. And we're using that in an algorithmic way that's been burnt into our heads in order to have a system by which humans can kind of just count forever, kind of can just go and list things forever. So this resets, we get double zeros, and we put a 1 here, right? And then we get all the way up to 999, and then we get to another digit, and then we just keep going, right? And this allows us to go forever. And so this is a computably enumerable set. This algorithm is something that's in all of our heads from a very early age. And that's what I mean by a computably enumerable set. If there's an algorithm, this is what I mean by there being an algorithm for listing out the stuff one at a time. So I want to show you some more examples of that because there's a bit of an art to this. So what other computably enumerable sets are there? So on the one hand, so other examples. So first of all, there are the integers. Z, which is n, but also negative numbers, negative whole numbers. So how can I list all of this? What's an algorithm for listing all the integers? So what's an algorithm for listing everything? It would be the following. How would you kind of write something? What could I tell somebody that would be like, this would get you, all of them? Well, I could start with 0. I could put it right here in the middle. And then I could kind of put a comma. I'll put commas here. And then on the right side, I'll say 1. But then on the left side, whenever I put a number here, so I'm just going to kind of count up in the same way that I did here, right? But then as I count up, I'm also going to count left in the same way, but putting negatives. So every time I put a number here, I'll put the negative version of it over here. 2, negative 2. 3, negative 3. And this is an algorithm. This is a finite, I just said it. I gave you a finite set of words, and from that set of words, you know how to, on paper, write out kind of a process that will, if you want, get to any number you want. Like pick any integer. You will eventually write out that integer if you continue in this format. That's what it means to be computably enumerable as a set. That there exists an algorithm such that anything in the set will eventually be hit if you follow that algorithm. So that's another example. A third example is the rational numbers. And so the rational numbers are, you typically denote it like with a kind of fake bold-faced Q. And what Q is, so a rational number is a ratio, is a thing, I'll just say, of the form, I'm leaving it open how you interpret what I'm giving you here, but I mean, if I give you two numbers, integers, I can just kind of write them like this, a over b, where a and b are integers, and b is not 0. So that's the rational numbers. So this is also a computably enumerable set, but I think you'll note that it's much less clear immediately how to give somebody an algorithm that will go through all of them. So what is that algorithm? So this is also a computably enumerable set, and here's why. What I can do is essentially, I just want to write out all pairs of two integers. So I mean, you could, this line doesn't matter, right? What I really want is that for any choice of A, I want to put every choice of B down here, and for every choice of B down here, I want every choice of A up here. That's sort of the kind of real goal. And for now, assume A and B are natural numbers. That'll make things more simple for now. And neither is 0. So let's do that first. So it's actually a lot simpler than I think a lot of people make it out to be. I think a lot of people sort of mystify this. That's probably textbook's fault. But let's just kind of think about it in kind of a practical term. Let's say A is 1. Well, if A is 1, I want to be able to pair that 1 with every possible B. And so I want to be able to pair that 1 with 1. I want to be able to pair that 1 with 2, 3, 4, 5, 6. And so basically you can kind of think about like dots right here. And each of these dots corresponds to one of these ratios. And then for 2, I have the same thing. And this will obviously keep going forever. This is an infinite table I'm making. But, for example, the dot right here, this dot would correspond to 2 over 4. And this dot right here would correspond to 1 over 5, and so forth, right? If I just kind of wrote out this table this way, and then I put the associated pair right in the right place on the table, then I would get everything. Do this again. So So, in a sense, I sort of have given you the algorithm. You could kind of imagine doing a process on paper in which you wrote a 1 here, and then a 1 here, and then a 2 here, and then a 2 here, and then filled in the associated rational numbers as you did that, and then that would give you everything. So in a sense, I actually kind of have already given you the algorithm, but you're probably not satisfied with that. If you want kind of if you want to know what the list of numbers actually is, if you want to kind of think about counting them one at a time, then you have to do what I tend to call the snake thing. So here's the snake thing. The snake thing is I think the more technical term for it is a dovetail search. It's a way to kind of go through a two-dimensional table in kind of a one-dimensional path. And the snake thing is pretty simple. You just start here, and then you go to this guy, and then veer down, and then go to this guy, and then veer down again, and then you go to this guy, and then you veer down another time, and then you go to this guy, and you veer down yet again, and then you go to this guy, and you veer down whatever number time, and then you go to this guy, and you veer down another time. Actually, I should probably, because at that point I would go to 5. I didn't write the 5, and I'll go down. You get the idea. You just kind of do like that. And that gives you the pattern. If you kind of write it out, you see the pattern of 1 over 1, and then 2 over 1, and then 1 over 2, and then 3 over 1, and then 2 over 2, and dot, 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 right? And so I think a lot of textbooks just write out this pattern and don't show you the picture, which is probably why it confuses some people. But that's all there is to it. This is the snake thing, and the snake thing does go through everything one at a time. And so that is an algorithm for listing out every possible rational number. So the rational numbers are computably enumerable. Well, okay, I haven't completely given you the thing, because if I've only given you for the positive rational numbers. So why does this also give you the algorithm for the negative natural numbers and B being 0? So I can account for A being allowed to be 0 by just simply putting a 0 here, and then kind of making this 1, and making this 2, and making this 3, and making this 4, and just kind of starting that 0 there. Obviously, I don't want to start the 0 here because B isn't allowed to be 0, so the 0 is easy to take care of. And then as far as the negatives, well, I can just kind of make a separate table over here. I can do the exact same thing that I did for the negative integers. I can make a separate table here, and then I can do 2 snake things at once, and then but basically alternate back and forth. The snake thing takes another step, this snake thing takes another step, and then this snake thing takes another step, and I just kind of weave the pattern together of the negatives and the positives, which is exactly what I did up here. So so that's the game. This is that's what computability, that's what computable enumerability kind of is in one sense. It's actually a lot of things, as we'll see. But this is one way to say what it is. It's also countability, because there's another aspect to this, which is that all computable, in a sense, I'm giving you an algorithm for writing it out, but another thing is happening at the same time, which is that it all kind of comes back to this. I sort of said earlier that this is kind of burnt into your retinas at a very young age. And in a sense, this is the fundamental kind of algorithm that we use to count everything else, because the whole point of this is to be able to count other things, right? That's why you're given the natural numbers. That's why you're given this, so that you can count other things. You're given this, and in a sense, we are using this in order to do this, because when I actually give you this pattern, one, this thing, and then this thing, and then this thing, there's a sequence there. I'm sort of, in my head, whether I do it explicit, whether I say it explicitly or not, I'm sort of defining a mapping of this is the first thing, this is the second thing, this is the third thing, this is the fourth thing. I'm defining essentially a function, a one-to-one correspondence between these counting numbers that I am given like a fundamental algorithm for very early in my life, and whatever I'm trying to count. So whenever I have a computably enumerable set, so whenever I computably enumerate a set, I am also counting the elements of the set. So that's kind of right now, it's not clear that those are two different concepts. So it's unclear if these are really different as concepts. The concept of computably enumerating a set and the concept of counting a set, how could that possibly be any, if I can count the set, then it's computable, right? Well, if you can count the set, that it's computable. But countability maybe isn't really the best word for what that concept is going to end up being. It's going to turn out that countability is sort of a more general concept than computable enumerability, but I think I'm making things a little too confusing. So I'm going to stop there for now, at least talking about countability, but we are going to touch on that concept. But before we move on, I want to look at some more sets. So we've seen some computably enumerable sets that were easy. Here's a less obvious. So here are some less obviously computably enumerable sets. Let's look at a few. So the first example I want to talk about is sets of natural numbers. Just all of them. Take the set of all sets of natural numbers. So, stuff like, 1, 13, 27, 8, right? There's one set of natural numbers. Another one would be the even numbers, right? 2, 4, 6, 8, 10, 12, ... The set of all of these, sets, that's what I want to computably enumerate. Every possible set of natural numbers. So is there an algorithm? So is there an algorithm for listing all of the possible sets of natural numbers? So I'll get the even numbers, I'll get the odd numbers, any pattern you want, any not pattern you want, anything that a random algorithm would give you. It just goes through everything. That's a lot less obvious. I think that, even the rational numbers here that confuse a few people, there's sort of an obvious algorithm that you can do to list them all out. This is almost natural, I think. But if you walk away from this video, and you should, think for a little bit. How could I possibly give you an algorithm that would go through every possible set of natural numbers, including the infinite ones? I think you're going to find that it's very difficult. Another one. So I'll call this example 1, and then I'll call this example 2 with an asterisk. Um, uh, Infinite binary strings. So infinite binary strings. So that is to say, stuff like, so I wrote out a couple of the objects as examples here. Obviously I can't give you the set because that would be saying it's computably enumerable. I just have to kind of write down a few examples for you. So one example would maybe be like, 0, 1, 0, 1, 0, 1, 0, 1, dot, 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 right? There's one. Another one would be just maybe 0, 0, 1, 1, 0, 0, 1, 1, dot, dot, dot. And it could be completely random. 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 0. Right? Every single one of these infinite binary strings. How do I generate all of them with an algorithm? It's kind of weird to even talk about, right? Because they're infinite. I can't write them down on paper, but like, can I think of even like some kind of assignment that would allow me to kind of think this way? It's not obvious. It's not obvious. And the reason I put an asterisk here is because the task of trying to kind of count all of these, maybe not even computably enumerate them, but just count these. How do I count these? How do I kind of assign a number? How do I denote like a first one? How do I denote a second one? How do I denote a third one? And I think honestly I just explained to myself sort of a way to kind of obviously intuit the difference between computably enumerable and countable. Obviously, in some sense, this can't be neither of these could possibly be computably enumerable because again, they're infinite. There's infinite sets, and so if I wanted to tell you how to write them down one at a time, you would never finish writing a single one of them. So it's kind of invalid to even talk about computably enumerable for stuff like infinite sets or infinite strings. But nonetheless, you can still think about counting them one at a time. You can still think about the task of assigning a first one, assigning a second one, assigning a third one. What is the first binary string? What's the second one? What's the 12th, right? And the reason that I put an asterisk here is because the task of counting this and the task of counting this are really the same task. So, and the reason for that is there is an obvious, there is an identity between every binary string, infinite binary string, and every set of natural numbers. A very obvious one. And that very obvious one is basically to do this. So let's just take this example. So I can look at this binary string, which is just alternating 0 and 1, and I can just kind of look at the index, and I can kind of make the set of things of numbers that have a 1 as the index. So there's a 1 in the second index, so I'll put a 2 here. There's a 1 in the fourth slot, so I'll put a 4 here. There's a 1 in the sixth position, so I'll put that here. There's a 1 in the eighth position, so I'll put that here. Oh wait, I just wrote down the same set that I wrote down here. This kind of is this. So if I give you a way, so if you can come up with a way to count all of these, then you've also come up with a way to count all of these. And so, the task, I'll write it like this, the task of counting all of the binary strings is the same task as that of counting all of the sets of natural numbers, including the finite sets, right? Because if I wanted a finite set, I would just let all but finitely many of these be 0. And it's also the same task as the task of counting the real numbers, but I'm not going to get into that. And so there's a few things I still want to do in this video. One is I want to note another thing, which is intuitively, it seems like this. And I'm saying it seems like. I'm going to try to convince you that it seems like. And this is not kind of a full argument, but it is worth, I think, noting at the moment. It seems like if the set of infinite binary strings is not countable, if there is such if there are sets that you just can't list one at a time, then the set of infinite binary strings is in some sense bigger than any computably enumerable set, or any countable set, because in fact I'll say countable instead of computably enumerable. And the reason for that is because if it wasn't, I mean, because think about it like this: say that it wasn't countable. Well, you know, it's not if it's not countable, then I can't kind of assign numbers one at a time. And so I can't, you know, if there's not a first one, if there's no way to kind of assign a first thing and a second thing and a third thing, then in a sense you have to sort of say there's too many things. And so in what we've just kind of deduced, or I mean, assuming that there are sets that aren't countable, and we're going to see, I'm going to show you explicitly why this particular one here, the infinite binary strings, that this isn't a not countable set. We're going to prove that. If there are uncountable sets, then there are different sizes of infinity, because in some sense you have to say that the rationals, you know, the set of rational numbers, this is an infinite set, and so is the set of infinite binary strings, but in some sense they can't be thought of as the same size. This has to be thought of as bigger. And so we've essentially derived or intuited that there have to be at least two notions of infinity. So that's one observation I want to make. And then one last thing I wanted to do in this video is I wanted to do one more example of countability that I forgot, or computably enumerability. So, so two more examples, important examples, don't leave, of computable enumerability. So two more important examples, and they're kind of connected. We talked about writing out, we saw this algorithm up here for writing out all of these numbers, and we noted that really what we're doing when we list out all these numbers, we're listing out sort of most of the strings that you can make out of this alphabet. And I want to kind of generalize that. That's going to be important. So consider trying to enumerate all strings, all finite strings from the alphabet. Let's just use the first three letters. Let's just use the first three letters of the alphabet. How many, how do I write out every possible finite string that I can make out of these three letters? And this is sort of going to be just kind of a formalizing of what I already did with the digits. We can turn to kind of look at what we did with the natural numbers and just kind of repeat that. And I think you'll see what I mean. So basically the algorithm is going to be a for loop. Essentially it's going to be, I'm going to be counting, and then for each number that I count, I'm going to write out. So there's a for loop here, kind of implicitly. So idea, for each n, i.e. I'm going to count through the natural numbers. So count through the natural numbers. And then for each number n, write down all strings of length n. So I'm going to kind of write down this. I'm going to write down all of them, and I'm going to go by length of the string. So it's kind of like for every possible length, write out all of these. So how do I write out all those strings of length 1? Well, that's easy. Here's one, and then here's another, and then here's a third. Done. Good job. We've got all the strings of length 1. Now let's move on to all the strings of length 2. Well, how did I do that for the digits? I ran out of digits, and then what did I do? I went back to the first one, and then I put another one here. And then I started to count again by the rightmost digit. So then I do AB, and then I do AC, and then I'm out of digits again on the right side, so I flip the A to a B, and then I flip this back to an A, and then I keep going. And now I'm out of digits again, so I flip back to an A, and then I take this to a C, and then C, B, C, C, and now I'm out of these guys, so I put an A here. I start, and that's it. This is the for loop that does the two. This is every possible two-letter word. And now now I start at the three-letter words, and that will go on forever. This will give you everything. So this runs through everything. And in a sense, you're even more familiar with this algorithm for this is called lexicographical ordering of strings. But it's also called the dictionary ordering, because you're more familiar with this method of listing things out than you realize, because it's exactly what the dictionary, any dictionary in any language kind of works this way. If you want to look up a word in a dictionary, it kind of goes like this. This is kind of just, that's what we're doing essentially. Of course, not all of these are words. In fact, none of them are. But this is a way to go through every possible finite string. And that's interesting because it seems like, okay, it's easy to write down every possible finite string. I can give you an algorithm for that. But again, infinite strings, that seems harder. And so there's one last incredibly important computably enumerable set that I can conclude from this. So this is when things are going to start to get a little bit meta here. So recall that I can write down a full description of a Turing machine on paper with a finite amount of text. I can just list all the instructions one at a time. Or, if you don't want to think in terms of Turing machines, you can write a Java program. Any program that you write in any programming language is a finite string. And so if I just kind of standardize the alphabet, say we're only going to use ASCII or Unicode or whatever, or just zeros and ones for that matter, so there's a one-to-one correspondence. So there's an identity, I'll call it, because it's the same kind of identity that we found up here between infinite binary strings and sets of natural numbers. It's the same kind of identity. I can make kind of a correspondence naturally between finite strings, and Turing machines. So, I can go through every Turing machine in the same way that I just did this. I can just do this, and then as soon as I find a string of text that is a valid Turing machine syntactically, so basically what I'm going to do, so i.e. Go through every finite string, and whenever we accidentally write down, whenever we find a valid string coding a Turing machine, that is to say, I've written it out in the syntactically formal way that I've kind of said this is how you write down a Turing machine, pluck it out. That will give you, this is a computably enumerable way to write out every Turing machine. So this is a computably enumerable way to list every Turing machine. So the set of all Turing machines, I'm making this a little long-winded, but it's incredibly important that we note this right now. So the set of all Turing machines is computably enumerable and also countable. I.e., by the Church-Turing thesis, what does this mean from the Church-Turing thesis' perspective? I.e., by the Church-Turing thesis, and don't worry, I'm not doing anything bullshit with it right now. I'm just going to note what this kind of means. If the Church-Turing thesis is basically saying that the Turing machine is a complete model of computation, it has everything, then what I'm really saying is that the set of all computable tasks is countable. So if we find that there are some sets that simply cannot be counted, then we've in some sense discovered uncomputability. Although it's a very cheap uncomputability, because again, these aren't really things that we want to be, we can talk about listing on paper anyway, or at least not the ones that are like patternless. But the point I'm making here is that it was important to note that we can, with a Turing machine, essentially list out every Turing machine. That's one thing that we can take away from this. And we can also take away from this that the set of all Turing machines is potentially kind of small compared to the set of all tasks that we might want to do with them. So we are starting to veer towards uncomputability. And in the next video, I'm going to show you why this set particularly, the set of all infinite binary strings, I'm going to show you why this set is not countable. And from that, from looking at how we did that, we're going to very naturally, actually, be able to construct for ourselves a problem that is not computable. And I actually said the next video, but I lied. That's probably the video after next. The next video is going to be talking about decision problems, and it should be kind of a quick one. But that's where we're going.